In this section, what we're going to be doing is linear approximation differentials. So this is going to start setting us up to go to optimizations and also set us up to do antiderivatives, which is integration. So we are going to use what we know to approximate solutions. We're going to calculate the error, and we're going to draw some graphs. So here's two examples that I have right here, in which here's my original function on the left-hand side. So this is my original function here. And I have a tangent line. Now, if I zoom in on that square, so that square that's zoomed in right here, this square represents all of this. So if I zoom in, that the approximate value of, say, 2.1 on my graph is 0.475. The actual value on my graph is I can just put the 2.1 in and it kicks it out. But I can use this formula right here to approximate it. The reason we do this is sometimes it's easier to approximate than it is to actually plug and chug. Now, where does that number come from? Y equals 1/2 minus 1/4 x minus 2. Where do you think that equation came from? Where do you think that equation came from? Yes. Yes, it's the equation of the tangent line. So we can use the equation of the tangent line to estimate. So we're going to use the equation of the tangent line to estimate. It's just the equation of the tangent line. Are you ready for this? It's right here. Just right here. Just, yeah, okay. All right, so good.
Will we always use what we do?
No, it's just because we are choosing something close to what we want. What we wanted is 2.1. So we're going to choose something close to 2 that we can easily plug in, so we chose 2. So the equation that we use is this. The linear approximation is going to be f of a multiplied by f prime of a, which is just the slope evaluated at a, and then minus x minus a. So we're going to use linear approximation to find the approximate values. Now, back a long time ago, if you wanted to find the sine of an angle or a cosine of an angle, or you wanted to know the square root of a number that wasn't a perfect square, you had to look them up in tables. So what they did is they had grad students across universities sit there and do a linear approximation, bam, to fill in those tables. So that's where you had to do it. I mean, you just didn't have, you couldn't get your calculator out and find the square root of 8. You just didn't. So what you had to do was you had to go to the table, and somebody spent hours and hours and hours doing this so that you could use the table. So your calculator is also doing this, but quickly. So if I'm asked to find the linear approximation of this, then I want to know approximately what 1.1 is. And the way I figure out approximately what the square root of 1.1 is I use that formula I just had, which is my linear approximation, L of x, is equal to f of a plus f prime of a, x minus a. Now a is the cool value. A is the value we know the value of, right? So when I look at the linear approximation of 1.1, my a is 1 because I can take the square root of 1 all day long. I can take the square root of 1 all day long, so my a will be 1. The a that we choose is going to be the one that we know the value of without any work. The x is what we're actually trying to evaluate. Okay? So in this case, I use a to be 1 because I know what the square root of 1 is. What I'm trying to evaluate is 1.1, so that's my x value. So that's x. So the first thing I have to do is I have to find the derivative of my function because I need to evaluate it at my given a. So I have to find f prime of x. So I take the derivative of the square root of x. What's the derivative of the square root of x? So this is 1/2 x raised to the negative 1/2. So after I find f of a, I now plug in, or f of x, I now find f of a. Now the a is the value that we know the top of our head without any work. In this case, it's 1. So I'm going to find f of 1, which is 1/2 1 raised to the negative 1/2, which is just 1/2. Okay? Now, I have this part of it. Boom, I got that. A was 1, I've got that. X is 1.1, I got that. What am I missing? I need to find f of a too, right? I got f prime of a right here. I just need to find f of a. So I could have started with that, but it's a step I need. So I need to find f of a. And so I put square root of 1. And so now I've got that. So I have all the pieces that I need to do the linear approximation. So L of 1.1 is equal to f of a is just 1 plus f prime of a was 1/2. X is what? 1.1, because that's what we're trying to chase, is 1.1. And then I subtract off, what was a again? 1. So my answer is 1 plus 1/2 multiplied by 0.1. Now remember, this was used back in the day without calculators. So what you would have to calculate then is you would have to calculate 0.5, which is 1/2, multiplied by 0.1. What is 0.5 multiplied by 0.1? 0.05, right? So this is equal to 1 plus 0.05, which is equal to 1.05. That's an approximation for. This represents the square root of 1.1 approximately equal to 1.05. Now what I want you all to do in your calculators is tell me what the square root of 1.1 is. 1.048. Pretty good approximation. We'll pick this up again tomorrow. So to go on to where we were from yesterday is we want to use the linear approximation to find the approximation of the given value when we don't know what it is exactly. Now, we have on the first example here is we are asked to find the f of 0.75. Now, when I see that, that really is in radians because we're in the calculus, so everything's in radians. So that is 0.75 radians, which is not pi over 4, it's not pi over 3, it's not pi over 2. So it's an approximation here. So we are going to figure out what is the approximate value using linear approximation of 0.75. Now, following what we did from before is we take first our function and we're going to find f prime of x. That's the first thing we do. Or the first thing we can do is we can put in our given a value, but I always like to find the derivative because they're exciting and new. So the derivative of sine is just cosine. Okay, so I found that derivative. And then I'm going to then find f prime of the a value. So I use a value that I know. A value is always a value that I know or I can evaluate quickly. So I'm going to find f of a. So f prime of a, which happens to be f prime of pi over 4 for this first example. So I'm asked to evaluate the cosine of pi over 4. This is equal to the square root of 2 over 2. So square root of 2 over 2. Okay? The other thing that I need for the linear approximation is I need to find out what I started out with. So I need to find f of a. So f of a, in this case, is f of pi over 4. So I put that pi over 4 in my original function, so the sine of pi over 4, which is just equal to the square root of 2 over 2. Now I have everything that I need to do the linear approximation. The linear approximation formula, again, is L of x is equal to f of a plus f prime of a, excuse me, and then x minus a. So I'll need each one of those individual pieces. X is, of course, the one that we are using to approximate. So when we're talking about f of x of a, or f of x, that's that number. It's not the a value. It's the one that we are hoping to find a value that's approximately equal to. So, sorry, what? So when we're asking to find f of x, or f of 0.75, I don't know what the sine of 0.75 is without a calculator. Or back in the day, I'd have to use a sine table, and this is how they made the sine table, the linear approximations. So they took values that they knew, because you know the sine of cosine of 45, pi over 4, the 60 and the 30 and the 90, and then they linear approximated all the rest of them for hours on end. Isn't that delicious? And then back in the day, so back when I was in high school, in the 80s, by the way, so it wasn't that long ago, all we had was sine and cosine tables. We didn't get to have calculators, because they had them, they're just so terribly expensive. We didn't have them. So this is what we did, is we just used the tables, but somebody at some point had to come up with these tables, and this is how they did it. So after you have done all of that work, let's plug in the things that we know. So we're asked to find L of 0.75. So 0.75. This is going to be equal to f of a, which we found in step 3, which is the square root of 2 over 2. And then plus f prime of a, which we found in step 2, which is the square root of 2 over 2. My x is what I'm trying to chase, so that is the 0.75, and minus the a, and that's the value that I do know, which is pi over 4. So now back before a calculator, I'd have to do the long and hard work here, but I'm not going to, as you all have calculators. So with your calculator, tell me what you all get. So with your calculators, tell me what you get when you do the square root of 2 over 2 plus the square root of 2 times 0.75 minus pi over 4. Tell me what you all get.
0.68207.
What is it? 0.68207. Is that what you all get? Okay. Now that's a linear approximation. And we want to know on this question as well, we want to know what the error is. The way that we find the error is the error is going to be equal to 100% multiplied by the approximate, which is 0.68207, minus the exact. So in your calculators, make sure you're in radians, do the sine of 0.75. Make sure you're in radians. 0.6816. Now, we put an absolute value on it just because we want this to be a positive number in error. If I didn't, then I would either find it's above or below. So if you don't put the absolute values on it, then if you get a positive, that means your approximation is larger than the actual. If it's negative, that means it's below the actual. But this time we're just going to put the absolute value on this. And then we divide by my actual. So somebody with a calculator, tell me what you get when you do that 100 and then in parentheses the approximation minus the actual divided by the actual.
0.03960.
Did you multiply it by 100?
Yeah.
So what is it?
0.03960.
So that's already in percent. So if you multiply it by 100, that's already in percent. So that's actually a pretty good approximation for the 0.75. Because my error is pretty low, it's less than 1. If my error is less than 1, then that's a pretty good approximation. How was that? Okay, please do a B and C. Please do B and C. Let's go ahead and go through B. So with B, I have to find f prime of x. So what'd you all get when I did f prime of x? No S words.
1 over the quantity x plus 1 squared.
Do you all agree that's the derivative?
Mm-hmm.
Okay, cool. The other thing I need is I need f prime of my a value, which is 1. So I put in 1 here. And what comes out? 1/4. What's the other thing that I need? I need f of 1. So what is f of 1? 1/2. Okay, the linear approximation for 1.1 is f of a, which is 1/2, plus f prime of a, which is 1/4. And then it's going to be my x. My x is 1.1 minus my a, which is 1. And what do you all get? So 0.525. Do you all agree? 0.525? Let's find the error. So the way we find the error is we do 100% absolute value of 0.525 minus. Put in a 1.1 into the original function. When you put 1.1 into the original function, what gets kicked out? 0.524. Divide that by 0.524. And what do we get as a percentage? What's our error? What is our error on this? 0.19. 0.19. How was that? How are you doing?
0.524.
So to find the error is we put the original back in. So we put the 1.1 into the original function and evaluate the original function. And when we did that, we got 0.524. And so we've got less than a 1% error. So it's not too bad. It's not too bad. How was that? You all want to do C or you want to move on? Do C? Okay. So let's go through C. We have to do what? We have to find f prime. What's f prime? All day long. We love that. We love e to the x. We have to evaluate f prime of 0. E to the 0. Well, what's e to the 0?
1.
We like that too. We have to do f of 0, which is e to the 0, which is still 1. We like that as well. So even though there is an e there and you all panicked, it really isn't that bad. Okay? This one is not that bad. So to find L of 0.05, this is going to be equal to my f of a, which is 1, plus f prime of a, which is still 1, multiplied by my x, which is 0.05, minus my a, which is 0. So what does this equal to? So 1.05 is what it approximates to. So let's find the actual and do the error on it. So my error is going to be 100% absolute value of 1.05 minus, what is e raised to the point?
1.05.
Is it 1.05?
1.05127.
1.05127 all over 1.05127. So what do we get as my error on this one?
0.1208%.
0.1208%. That's a pretty low percent, so it's a pretty good approximation. How was that? Is that okay? Now on the next ones, we're going to do the same kind of thing, but we're going to have to choose our a value, right? So we have to choose our a value. I've seen that. I've seen your face all wrinkled up like that. So I'm going to choose an a value of something I know with no work. So the tangent of 3%. Do you think I'm going to use pi over 4? What do you think I'm going to use that's close to that I know? 0. So for this one, I'm going to use a is equal to 0. What about b? Cube root. Well, I need a perfect cube that's close to 65.
64.
So I'm going to use 64. What do you think I'm going to do for c? I need perfect squares. I'm going to do each one individually. Looking at the numerator, what's a good replacement for a perfect square in the numerator? 4. And then what's a good approximation replacement for the denominator? 25. Because 29 is closer to 25 than it is to 36. Now, let's go back and actually figure out what the functions are as well. So on these, not only do we have to figure out what a was, but we have to figure out the function. What do you think this function is going to be, f of x? Tangent of x, because we're doing replacements for the angle, so it must be the angle is where the x will go. What about the next one? What do you think my function is going to be? Cube root x, because I'm finding replacements for the value underneath the cube root. So this must be f of x is equal to the cube root of x. So what do you think about c? What am I doing replacements for? The square root. So this is f of x is equal to the square root of x. Which one of these would you like to do? Okay, do the first one. So let's take a look at a. I need to know f prime of x. What is f prime of x? Remember tangent x, what is it?
Secant squared x.
So this is going to be a secant squared of x. I need to know f prime of 0. So the secant squared of 0. Secant is the reciprocal body of who? It is the reciprocal body of cosine. It's 1 over cosine. So I just find the cosine of 0. What is the cosine of 0? So I square that and I do the reciprocal of that, which is just 1. The other thing that I need to do is find f of 0. So I need to find the tangent of 0. Well, what's the tangent of 0?
0.
We like that. So now I'm just going to use my linear approximation formula. So L of 3 degrees is equal to f of a, which is 0, plus f prime of a, which is 1. And then I have my original, which is 3 degrees, and guess what I need to put this into?
0.03.
I need to turn it into radians, because everything in calculus is in radians. So what is it in radians? So 0.03, is that what it is in radians? Do you all agree that's what it is in I don't know. Okay, so this will be a moment of reminding ourselves how to go from degrees into radians. So you take your degrees, in this case it's 3 degrees, you multiply by pi over 180 degrees. So do 3 times pi divided by 180. This will give me my radian. So what is it in radians? Is it 0.03? So it's 0.05235? Is that what you all get? I don't know. You tell me. You.
1 over 65.
Pi over 60.
Pi over 60.
Yeah, this is what we got, yeah.
Okay, well, could you tell me the approximation? Is that?
That's the approximation.
Okay. So the approximation is what we need to put in here, which is going to be 0.05235 minus, well, what does I start out with? I minus my A value. My A value was 0. And so I end up with 0.05235. That's what the linear approximation of 3 degrees is. Now we're going to find the error. Remember, somebody somewhere in the 20s and 30s, early turn of the century, sat and did these tables for us because they were delicious. Let's figure out what the error is. The error is 100, and then it is the absolute value, 0.05235. And then in your calculators, either go in degrees or radians, it doesn't matter, make sure you're consistent though. Tell me what the tangent of 3 degrees is, the actual value.
0.05240.
All divided by my actual. So what is my error? What is my error on this one? What is my error? Anyone? Calculators? You all have calculators. I don't have calculators. Someday I'm going to come to class with a calculator and it'll blow your mind. What do we got? Anyone? Oh, anyone? 0.0918%. That's actually really good. So whatever grad student had the opportunity to do this had a pretty good chance of getting it close to the actual. Because who wouldn't want to spend their whole day doing that? Okay, now we're going to do the same thing, but we're going to call them something slightly different. So we're going to call them a differential. It's the same thing. So I'm going to really focus in on f of a plus f prime of a x minus a. And all I did from this original one here, so from here to here, is I just rewrote it. That's all I did, is I just rewrote it. So I have my f of x minus f of a. I just took the f of a to the other side of the equal sign. That's all I did. And the reason I did that is because f of x minus f of a, those are output values. Those are y values. So since those are y values, then this side of the equal sign is my change in y. So dy, or delta y as you see it. F prime of a, x minus a, this is my change in x. So I have my change in x is equal to my change in y. That's all I did. The reason I do that is I can replace f of x minus f of a as delta y if I need to. Delta being that triangle, just delta y. dy is another way we can write it. And all I'm doing is I'm just replacing some of the notations. Okay? So assume f is differentiable on some interval, so some x value to x value, and it has some point in there that we actually care about. We're going to call that a. Then the change in the values of x between the points a and, say, a plus something close to it is approximately equal to f prime of a delta x. at prime of A delta x. So long as that A plus delta x is in there. So if I chose a delta x that's say 6, and my interval runs between 1 and 2, obviously the value I choose plus 6 is not going to be in that interval. So the delta x plus A has to be in the interval I'm still looking at. These are really straightforward. Is we want to approximate the change from 2 to 2.01. So all we have to do is figure out what delta x is. What is delta x? Well, delta x is the difference between where I started and where I'm going to. So my delta x is going to be 2.01 minus 2. Started at 2, and I ended at 2.01. That's my delta x. All I have to do now is find p prime of z. So I have to find that derivative. And so I have 1,000 e raised to the negative z times, or divided by 10. So this is going to be 1,000 e raised to the negative z divided by 10 times the derivative of negative z divided by 10. So this is going to be multiplied by minus 1 over 10. This is d dx of negative z over 10, which is the same thing as negative 1 over 10 d dx, or it should be dz, sorry, d dz of just z. This is with respect to z. So dz. The derivative of z with respect to z is just 1. So that's why it is the negative 1 over 10. So I still have to find the derivative, just like I did on my previous linear approximation. I still have to find p prime of a. My a happens to be 2. That's a 2, not a z. I put a bar through my z, so that's a 2. So I still have to evaluate it as I did before. So 1,000, oh, let's clean that up. So it is 1,000 divided by 10, so that gives us a negative 100 e to the negative 2 over 10. So I still have to do that part of it. And what do you all get in your calculators when you do that part of it? Give it to me in like 2 decimal places. Negative 100 e raised to the negative 2 over 10, or negative 1/5.
Negative 81.87.
Do you all agree? Negative 81.87. So it's still the same thing as I did before with my linear approximations. I still need to do that. The difference is that now delta y is equal to my a value, which was 2. I'm sorry, it is the delta x. My delta x, which was here 0.01, so I take 0.01, and I multiply by that by the negative 81.87, and that's it. And that's the linear, that's the approximate delta y. That's all you have to do. That's it. So what do you all get when you multiply this?
Negative 8.
Negative 8.
1873.
1873. Okay, how was that? Negative 8.1873.
Negative 81.87.
Yeah, that's a 7. Yes.
Since it's multiplied by 0.01, should it be 0.818? That's what I got.
Okay, thank you. Yes. I'm just listening to what you all are saying.
Oh, yeah.
Don't lead me astray.
I multiplied by 0.1. It's okay if you lead me astray, but don't lead me astray too often. I'm gullible. I'll listen to you. So it is negative 0.8187.
That's it. That's all you have to do on these. This is not bad. So which one of these would you like to do? Well, you got to do B. Look at that. Please do B. So let's find our delta x. So this is going to be 3.05 minus 3, which is 0.05. So I find my delta x. I'm going to find my derivative, but before I find my derivative v of r, I'm going to put in the things that I do know. So they're giving us the h value. So the only unknown is the r. So this is going to be 4, because that's the h they're going to give us, pi divided by 3 and r squared. And the only reason I'm writing it that way is so that just makes it easy for me to find my derivative. This is not related rate, so it's not going to be with respect to time. It's just going to be v prime of r. So v prime of r is equal to 8 pi over 3 times r. So that's nothing new. And now we have to evaluate it at the r, which is 3. That's our a value, which we evaluated at 3. So v prime of 3 is equal to 8 pi divided by 3 multiplied by 3. So this is just going to be 8 pi. Okay. Now once I did that, my last step is just to multiply it by my delta x, and I'm done. That's it. So delta y is equal to delta x f prime of a. And in this case, my delta y is going to be equal to 0.05 multiplied by that 8 pi. And that's it. So what do you all get?
0.4 pi.
What is it?
0.4 pi.
0.4 pi. How are these? Are these okay? Are these awful? Would you rather go back to doing implicit differentiation? I forgot to give you a quiz. I'll have to give you one tomorrow. That reminded me. I have to find another one. Okay, this is the last part of this section, which says, considering the following functions and express the relationship between a small change in x and the corresponding change in y in the form dy is equal to f prime dx. So all I'm asked to do is find dy is equal to f prime dx. That's all I'm asked to do. The reason we're doing this is because when we get to the end of this chapter, we're going to start undoing derivatives. So we've got to get used to the notation. So all I'm asking you to do is just do our regular derivatives. So normally we do dy dx is equal to, and this is going to be the chain rule, so it is going to be 2 sine x cosine x. And that's what we normally do. And then we replace dy with y prime if we're inclined. This is what we have been doing. Now, what we're asked to do is just write this as dy is equal to 2 sine x cosine x dx. And that's going to help set us up for integration, which is undoing derivatives, which happens toward the end of this chapter. So that's all I'm asking you to do B and C. So please do B and C, and then we'll go into the next section. Okay, so let's do B. So dy dx is equal to, I'm going to do the derivative of the numerator, which is just going to be 1 times the denominator, 4 minus x. And then minus the derivative of the denominator, which is going to be negative 1, multiplied by the numerator, which is x, 4 plus x, all divided by the denominator, 4 minus x, the quantity squared. Do you all feel like cleaning this up algebraically? I don't either. I don't feel well enough to do that. So my answer is dy is equal to, I feel this urge to clean it up algebraically. I'm sorry. So what does it clean up algebraically to?
1/4 minus x squared.
And then dx, and that's your answer. That's it.
So if you're doing the homework and you end up with 1 over 4 minus x squared and it being marked wrong, it's because you forgot to write dx. Yes? I don't know. Is it 4? Is it 8? Is it 8? Thank you. I don't feel well enough to fight you. If you told me it was 62, I'd say okay. I'd be okay with that too.
It is 62.
Okay, cool. Okay, last one, and then we're going to talk about the next section. Okay, so normally I would write again dy and dx is equal to 1 over 1 minus x multiplied by -1. And then, so my answer is dy is equal to -1 over 1 minus x dx. Again, if you don't write dx next to it and you're being marked wrong, it's probably because you forgot to write dx next to it. So be aware of those on this homework. Any questions on these? How are we doing? Okay, so let's start.